Right, so let's begin with an example. So let's suppose T of x, y, z is equal to x plus 2y plus 3z, and then y minus z. So define T to be that linear transformation. I guess I haven't proved it to linear transformation just yet, but how could I prove it to linear transformation? Not too hard, I just like this, right? This is the same as the matrix 1, 2, 3, 0, 1, minus 1, times the column vector, x, y, z. As you can see, this is a linear transformation P, which takes as its domain R3, as its codomain R2, right? And this character over here, right here, you have the standard matrix of T, right? Standard matrix of T, which we denote by bracket T, which again is a box of numbers we call matrix. In particular, it's an element of R. It goes backwards, right? So if you go from R3 to R2 as you're mapping, your standard matrix is in fact a 2 by 3. All right. Start with the example. Yeah, Dr. Franklin.
Yes, that's correct. So basically, everything we did in Calc 3, if we had known, we could have written matrices and it been like exactly the same.
No.
No? Oh.
In fact, matrices only covers just a little bit of Calc 3. I mean, I will come back to this later today. I mean, would I like to have linear algebra as prerequisite for Calc 3? Absolutely. Will they let me?
But like,
No.
but like, okay.
You know, I'd like a lot of things. I'd like for tax day to be the day before election day. I mean, there's lots of things I'd like. Here's another
You'd actually
one.
have to like get people elected. It would be a disaster.
Yeah, I think if you take aid from the government, you shouldn't be allowed to vote. That's another belief I have.
Well, there you go.
Okay. Now that we've documented this evidence on YouTube, I can never be elected in any sort of beyond city council sort of role.
Well, you also lose your credibility as a professor in college because of your conservative beliefs.
Is that right? This isn't conservative. All right, so S of
Well,
kidding. A comma B. I don't know. What do you want here? Let's say A plus B, A minus B, that'll do. All right. Now, of course, I can also write this as a matrix, what?
1, 1, 1,
Yeah, 1, 1, 1 minus 1 times AB, right? And as before, you can identify the standard matrix of S as being this. Of course, this is a 2 by 2 matrix, right? And let's see here, S is a mapping, what? S is going from where to where?
R2 to R2.
R2.
Yeah, S goes from R, takes in a 2 vector, spits out a 2 vector, R2 to R2. All right. So now, the question I'd like to ask is, find the composite of these mappings in each way which makes sense. Find the standard matrix of the composite of the composition of the maps, and find the formula, if possible. So there are two things you got here. You got an S and a T. So you can either think about what are your choices. Your flavor choices here are somewhat limited. You either can think about S composed with T for case 1, or case 2, you could think about T composed with S.
Oh, yeah.
Can't you only do S composed T?
I said if possible, yes. So you said only S composed with T? Why?
Because the matrix multiplication won't match up.
Well, you're getting ahead of me a little bit, but how about this? T goes from R3 to R2, right? That's T. T comes first in the composition, actually, right? And then whatever we feed into T has to go into S, right? Then R2 to R2 is, so the composition S composed with T makes sense because the output of T is something reasonable to put into the input of S, right? In other words, the values of the T mapping fall in the domain of the S mapping. So the composition S composed with T makes sense. On the other hand,
These two doesn't make, two cannot happen.
yeah, on the other hand, this, we've got our S, we're going from R2 to R2 with S, and then this doesn't even make sense, right? T doesn't take, this right here is not even the case. T doesn't have R2 as its domain. That composition does not make sense. This is not really a linear algebra comment. This is more of a pre-calculus comment. Like, how can you compose two functions? You can only compose them if the image of the inside function actually falls in the domain of the outside function. Otherwise, they're hard to compose. Okay, so now I've got it.
Arguing impossible.
Yes, impossible. Possible falls under the general umbrella part though. Let's hear. So
Your homework really is hard, and your quizzes are really hard. By the definition of the impossible are hard. Well, anyway.
I'm ignoring you guys. My custom. Okay, so S composed with T. X comma Y comma Z. So I'm just going to work it out the annoying way because it's good for you guys to see this once. So this is S of T of X, Y, Z. Right? Which is what? This is S of, let's see, T of X, Y, Z was defined to be X plus 2Y plus 3Z, comma Y minus Z. That was what I defined at the start class today. And then basically we make a substitution, right? You think of X plus 2Y plus 3Z as being my quote unquote A. You think of Y minus Z as being my quote unquote B, right? And then you just plug back into my definition for S, and out pops the formula for the composite, which is, let's see here, A plus B, so I have X plus 2Y plus 3Z plus parentheses Y minus Z, comma, X plus 2Y plus 3Z minus parentheses Y minus Z. One more step to clean it up. This gives me X plus 3Y plus 2Z, comma, X plus Y plus 2, wait a minute, no, plus 4Z, right? Now what's the matrix for the composite then in view of this formula? The composite is going from R3 to R2, so we expect a 2x3 standard matrix for the composite. So all right, so we got 1, 1, 3, 2, 1, 1, 4. So allegedly, I mean, I hope if I haven't made a mistake, I hope you would have had the common decency of pointing out my mistake by now if I had made one. What's that?
Because you're ignoring me.
Wait a minute, why am I asking what did you say? Stick with my mode. You're in my mode. Stay in my mode.
I'm done with you.
People from one day. I can't stay in my mode.
I'm built for everything I need to.
No. What comes next? Oh, yes. So check this out. If we take the standard matrix of S times the standard matrix of P, what do we get? I mean, I'm just saying, do it, right? So standard matrix of S was 1, 1, 1 minus 1, right? Standard matrix of P is yeah, 1, 1 minus 1, 1, 2, 3, 0, 1 minus 1. All right, so what do we get? So this is a 2 by 2 times a what? 2 by 3, so the output will be again a 2 by 3. These matrices are multipliable. Very good.
Dr. Cook?
Yeah.
Wait.
What? Wait a minute.
Did you do the wrong,
Moving along.
like, did you do the wrong T? Or is that the, oh, it's the other T. Oh, never mind. I thought it was like the new, never mind. I'm sorry.
So the first column, 1, 1. The second one is 3. 2 minus 1 is 1. Then I've got 3 minus 1 is 2. 3 minus a minus 1 is 4. Check it out. That's exactly what we found by just you know, plugging in and composing the formulas, right? 1, 3, 2, 1, 1, 4. So, as a pragmatic comment, all right, so if you define the formula for composite, right, what can we do? Simple method is what? Yeah, just multiply the appropriate standard matrices in the appropriate order, right? Now, of course, this is not an accident, right? I mean, this pattern we just observed holds in general for any two linear transformation which can be composed. We proved at the end of the last class, in fact, that the composite of linear transformations is once more a linear transformation, right? So therefore, we know that a matrix exists which represents it, right? It can be induced from a specific matrix, which we call the standard matrix of the composite. And I'm about to prove, in fact, that this example generalizes, all right? So let me go ahead and do that. Without further ado. So here's our cross theorem. Let's say if T is a mapping from, I don't know, Rn to Rp, and S is a mapping from, say, R. Let me make that an M. T goes from M, as in mommy, and S goes from N, as in nanu, to RP, as in pizza. Sorry, good at pizza. Okay, so can these be composed? If so, in what order?
S composed.
Wait, but
Yes, S composed with T. Very good. Then S composed with T is mapping from Rn to Rm is linear with the standard matrix of S composed with T equal to the standard matrix of S times the standard matrix of T. There you go. That's the theorem.
Dr. Cook.
okay,
Yeah,
okay.
but the-
P should be on the first
Yeah.
one and S.
It should be the domain
Or vice
of-
versa.
Should be from RP to RN, right? Or one of them
Yes.
should be flipped.
Oh, I'm T composed with S, sorry.
But like it's still.
Even
but-
so-
Yeah,
it's still
it
the end of
takes,
each
they
one.
both map to RP from a different one,
Oh.
so you can't take.
So I was supposed to put the P here was what it was.
Yeah.
I didn't say anything, he's already said so much.
No more questions for a second. Wait. I wanted this to be N. I want this to be P. I want this to be P. I want this to be M. So I can start with S. So that would be T composed with S. S composed with T composed with S rather. So S goes from here to here, P to there, goes to there. All right, give me a second here, and then I'll take your questions. I hopefully have answered them at this point. Yes?
I was just gonna point out, it's probably because you messed up your notes.
Oh, yes. I mean, I'm a creature of habit. Yes. I actually once got away with making this mistake in a poster presentation. I still won second prize. No one noticed. Many faculty judges looked at my very large, wrongly composed maps and did not pick up on it. This is why some mathematicians write composition in the other way. It's partly it's confusion. Okay, let me go on, because we're talking about that interesting. Proof. First of all, T composed with S is linear. Transformation. Hence, T composed with S exists by fundamental theorem. Theorem of linear algebra, right? Now, I may not even need that for this proof. I mean, I may provide the existence of the matrix of the composite just by the calculation I'm about to show you. But anyway, it's worth saying. We've already proved that in the last class. Okay, so then what? What I'm going to try to do is to show you that these two matrices are equal. So what's my game plan? My game plan is to show you that they have the same columns. So what I'm going to do then is I'm going to look at T composed with S. No brackets. So the composition of T composed with S acting on, let's say, EJ. All right? So that's supposedly what? T of S of EJ by the what? Definition of composition, right? Now what can I do? I can write S of EJ as the standard matrix of S times EJ, right? So this is what? This is T of the standard matrix of S times EJ. But what is T of something? I mean, if it helps you, I can make an intermediate step. I can call this thing baloney. I mean, whatever. Call it V. So you got T of V. Fundamental theorem of linear algebra says what? This can be written as the standard matrix of T times V. Right? Again, fundamental theorem of linear algebra.
So it would be the standard matrix of T times the standard matrix of S and J.
But this holds for all J. J equals 1 to n, hence the matrix of T composed with S is equal to the matrix of T times the matrix of S. There you go. I think this is easier than the proof I currently have in the notes. My proof in the notes suffers through some index calculations and such. If you try to look at it, it's a little more technical. Yeah.
Is it sufficient to just say that that just by the fundamental theorem of linear algebra?
Yeah, I should be saying that over here. This is definition, thank you, Christian. Definition of composition. You're right, my proof is incomplete. This is again using the fundamental theorem of linear algebra. And here I just made a substitution. In this step, again, I'm using the fundamental theorem of linear algebra, which we may abbreviate as FITLA, if you like. Yes, sir.
When we're doing proofs for tests or homework, are we allowed to write it out like that, where you have the reason that you're allowed to make that step to the right after a colon?
Mm-hmm.
Okay.
Yeah. I think that proofs in this sort of stacked equation format, especially for this kind of material, are easier for the reader to understand than, say, sentence formatted sometimes. You know, as always with proofs, the question is what's your audience, right? For some audiences, there doesn't need to be a proof of this because it's something they already know. For others, not you guys, I would actually have to write it out in terms of A11, A12, and then another matrix, B11, B12. I mean, oh, truly awful. But, you know, I mean, proof, what's the appropriate proof? Always depends on the audience. For me, I showed you implicitly, when I give you proofs in here, what I think is a decent proof, what I'd like to read. So, I mean, highest form of university education. When I tell you something, I tell you to tell me back. But anyway, if you know, that's a really, no, I mean, my proofs can be improved on, for sure. Like, my proofs are not always minimal. There's certainly room for improvement, but there are occasions in class when we've been hurrying, right? Like, I say things in words when I'm talking, but I don't write them on the board, right? I can't grade your thoughts, so, you know, you understand that. But you have my notes, right? So you have picky, annoyingly detailed proofs of those things. With that, I will shut up about that. Any questions about this? Yeah.
EJ is the same thing as EI, it's just you felt like using a variable.
J and I, these are just indices. So.
Yeah.
So just a word or two then about linear subspaces. So you might take this as a definition, at least a temporary definition. A k-dimensional subspace of Rn is something like S equals to the span, well, excuse me, it's let's say W equals to the span of S, where S is a set of k linearly independent vectors in Rn. That would be a subspace of Rn. Now, you can also talk about in a fine, you know, a k-plane, you might say, in Rn is of the form x naught plus w, where w is a k-dimensional subspace of Rn. Now we have special language for certain values of k, right? Like what's k equals 1? What's the common vernacular for k equals 1? What 1? No. That'd be 0.
A line.
I don't know if my definition allows for it, but what's that?
A line.
A line, yeah. It's a line. Now, if it's a subspace, that makes it a line through the origin, right? If it's just a line, it could be a line. It doesn't have to go through the origin, right? It can be shifted. So, you know, basically a typical point looks like this, right? X naught plus t times v. But you should recognize that as exactly being something in the, you know, t times v is the typical thing in the span of one vector, right? Like if I say span of v, what is that? Span of v basically is just tv such that t is an element of the radius, right? So that's a line. Yeah.
The x0 plus tv, didn't you say that was an affine space, not a line?
It's a k line. I mean, what I'm telling you is there are two kinds of lines. There are those that go through the origin and those that don't. So when I say line, I don't assume it goes through the origin. So I'm talking about the k-plane.
Okay.
Let's see, your k equals 2 is just a ordinary plane, right? I guess the difference here is it could be living in 10-dimensional space or something, right? It's inside Rn, you know? But what makes it a plane is that it's built from two linearly independent things, really. And so a typical point would look like this: x is equal to x naught plus, say, u times maybe s times u plus t times v. In other words, you know, if I have the span, if I have the span of two vectors u and v, that basically looks like su plus tv such that s and t are real numbers, right? That's the span of two vectors. Set of all possible linear combination of two vectors. That's how you set up a plane. Yes, Bailey?
The green is bad.
What?
The green.
Green is bad?
Yeah.
I thought we had better camera now. Green is still evil?
Yeah.
Well,
Yeah, it doesn't show up well.
Can I just like trace over?
all right.
I mean, it gives us a chance to catch something else, I guess. Not that we need catching up on this. So, the homework has a single point in it in the grade right now because it's just to say and indicate that we have turned it in, right?
Yeah, I wanted to, I was just being lazy, seeing whoever has not turned in the homework doesn't have that point there. But of course, I would hope most of you make more than 1 point on the third mission, yes. I think that's
There will be somebody.
Yeah, I'm pretty sure that's going to happen. Let's see here.
What will the solution be?
Good question. Did I post it?
Yeah.
Offline.
What's that? I mean, I will have it. I mean, I have it scanned. I can post it. It should be posted today. If it's not already posted today, it's because I forgot. And in fact, if you ever feel like it should be there and it hasn't been put there yet, you should just like send me an email. More often than not, I just forget. You know.
I'll make sure that
So, I mean, you get the idea. What is it? I mean, and so if you go back and you think about those parametric formulas from Calculus 3, you can see that that was basically a point plus the span of one vector. This would be a parameterization of a plane which has u and v as tangent vectors for if you've had Calculus 3.
Actually, one
Yeah.
more question. For k equals 0, it would be x equals x0.
Yeah, I think k equals 0 is, that's fair. K equals 0 would be, oh man, the ruined marker. Would be just x equals to x naught, right? And so we're talking about, I suppose, the span of nothing, what's the span of nothing?
Nothing.
Is it nothing or is it 0?
But 0 is nothing.
0 is not nothing.
There's
Zero is
difference
something.
between the empty set and a 0.
Like, for a real world application of that statement, you have a bank account with $0. You have no bank account.
That's true.
There's the difference. One of those zeros can cost you. I feel like there was something else I was going to tell you guys at this point. It will come to me soon.
And like, one more question actually, for anything like K3, K4, like you're just adding like another like two variables, one fifth
Right.
relation.
Yeah, we don't
This
really
man
have.
is like,
You've had Calc 3, right? So we don't really do much with parameterized volumes, right? We do surface integrals. So there's a place in Calc 3 where you look at how to like parameterize a surface, right? Which basically means that you have a mapping, that the image of that mapping is the surface. There's not really a place in Calc 3 where we talk about, too much anyway, where we talk about the image of a function of three variables being the volume, right? But that would sort of be the analogy here. A three plane would actually be a volume.
all right.
It'd be a three-dimensional subset of something. Yes, Landon?
What do you mean by like, is that just
Say
say
it quick.
k minus li? Is that what that is?
Linearly independent.
So
Linear.
there's k number of linearly independent.
Right.
Okay.
Oh, not mine. No. I don't know what mine is linearly independent would mean. I have not, nor do I intend to define such a concept. Oh, they're writing on the other side of the wall. Come on. So you're like, this is a linear algebra course. We should see applications. Feel your pain.
You know, what's your birthday? No, this is random, but like, I mean,
It's my birthday.
I want to give you like more stickers for your laptop.
Oh, I have more. I got some Disney stickers. I got to put on it. Here.
I'm also trying to kill time while we wait for projectors to come up.
So, what time do you?
What the time did it? There was never enough time. There was never enough time, so I decided to fill all the time I was left anyway.
All right.
It sounds like a perfect villain, like some weird, multi-dimensional.
So linear algebra.
All right.
Algebra, yeah. Probably so strong, but.
I guess I should have actually gone to the index, so sorry for this. Okay. All right, so some applications. It might be nice to see. We'll talk about some applications here for a minute. Jumping back to chapter 3 for a bit. So what do I put on the test? Like, roughly speaking, is what I test you on the homework. And, you know, the quiz also gives you a sense of what's important, right? Now, what's not on the quiz and what is important is all these little proofs we've done in lecture. Proof that the identity matrix times any matrix is the matrix again. Proof that matrix multiplication is distributive. I may not have actually done that in class, but that's a good example. You know, all these little proofs we've done, those are all fair game. I wouldn't put them on the quiz though, because your quiz is take-home. So, you know, I don't take any particular joy in you copying it from the notes and into the proof, but I do take joy in you knowing it when I ask you it in class. Yes?
I noticed on the missions, there was none of these like giant proofs where you build like a matrix to prove something, but you still probably know it, right?
Ask me again after class. I'm not sure what you mean. Okay, so here's one really interesting class of matrix example. These are called stochastic matrices. So basically the idea is you can study some population which is fixed, all right? So we have some net population. In this case, I start with 1,000 mice. IK is the number of infected mice at the beginning of week K. NK is the number of non-infected mice at NK. And this matrix right here, it basically, it stands for, like this first column does what? So if I take this vector times that, I get 0.2 times 100 plus 0.1 times 900. So like 0.2 times 100 does what? That tells me what? See, so there's an 80% probability that a mouse will overcome the virus, and there's a 10% likelihood a healthy mouse will become infected. Let's see, which one is infected? So
The V matrix is I.
yeah, I was trying to think what the.
Oh, it's right there.
So we start with what, 100 infected and 900 non-infected, then we go to 110 and 890 because what happens? 20% of the infected might get better, right?
No, they stay infected.
Oh, they stay infected, I'm sorry. I can't read. Yeah, 80% probability that they will overcome the virus, which means that it's a 20% chance that they will stay infected. Because it's an either or kind of thing, right? So these stochastic matrices, they're really cool in the sense that like there's a really nice pattern. The sum of the columns have to be 1. See? 0.2 plus 0.81, 0.1 plus 0.91. That basically will preserve the number of things. And if you keep doing this, you'll see something neat. It will, you keep going and going and going. Eventually it'll reach some sort of like stable equilibrium. In other words, there will always be a certain number of sick and a certain number. There's some kind of balancing between infection and non-infection for this kind of problem. That has significance. So I mean, that would be something like, you know, the kth and the k plus 1th step are essentially the same. That would be the steady state. So if you take the limit as k goes to infinity, then you end up with this equation, you know, x is equal to p times x, right? But if you put it on one side, you have to solve this equation, p minus I times x equal to 0, and you end up getting 111.11 and 888.88. So I don't know what that means in terms of, I guess you can't have like an 11th of a mouse.
11th repeating.
I guess that would mean that if you really, really believe in this model, there'd be something like 111 and 889, or maybe there's 888 and 112, or I don't know. I can't
Maybe
do
that
math.
one math is
I can't do
infected
math.
and non-infected.
Anyway, so that's a stochastic matrix in a nutshell. Another application, the diagonal matrices. This is a silly example. I'm going to go on past it. This is essentially the same kind of thing. I'm talking about demand for doorknobs and demand for yo-yos. And what is this going on here? Suppose the demand for doorknobs halves every week. Oh, who cares? This is a stupid example. Let's go on. Who wrote this?
This is my favorite.
Who wrote
part of
this?
linear
You.
algebra.
What's that?
This is my favorite part of linear algebra. I love stochastic matrices.
No, I mean, I'm not saying stochastic matrices are stupid. I'm saying that that example is stupid.
I also like doorknobs.
Oh. That was fun. This example is a little more fun. So naive encryption, basically the idea here is take your favorite message, convert it to the alphabet code, 1 through 26, right? Then, so you take that message and put it into, say, chop it up into 3 numbers at a time, right? So, for example, if I had the message,
How can I sabotage this?
cat, that would in alphabet code go to what?
3, 1,
18.
18, wow. Found your calling. Oh, is that just, you just made that up?
It's not,
Sure.
it's not 18, it's not 18. It's 20. Oh,
It's
is that-
20? Chris. Thanks, Chris.
You just say it with confidence.
Thank you for.
I was almost impressed for a second.
That is true. If you're ever a high school math teacher, you can just like recite 100 digits of pi. As long as you memorize the first 10 correctly, nobody can call you after that. I mean, unless they've got a laptop, and maybe by the time you guys are teaching, high school math, all the students will have laptops. We'll have completely slim.
Well, I want those like desks that are like computers, like an Ender's Game.
So what I do is I just desks that are computers.
Like, have you read Ender's Game? Anyway, get to your problem.
All right, so this is what. Can you guys help me multiply? Oh, I'm using green again. I'm so sorry.
She's not
I will tell you this. I will admit this. Green is my favorite color. All right, so
Really?
up to understand. So what do you got? 3 minus 20 is what? Minus 17. And then what's this? 18 times 18 plus 2 is 20. 20 plus 60 is 80, right? But then you work mod 26. So what you do is you just convert these all to 2 is fine. 26 add, minus 17 add 26, you get what?
9.
9. Okay. To get that back into between 1 and 26, let's subtract what? 52?
78.
78, yeah, too much. So that's 2. 2? That can't be right.
It's 54.
How many?
54? No.
What do you say, 78?
I don't.
Okay, 26, 32,
That seems right.
48, no, 50.
Yeah. So I get 2 for this as well. What? Oh man.
I mean, with the decryption, it might be different. You might find it.
No. I mean, this is an invertible map. It should be 1 to 1. I can't map both 3 and, I shouldn't have this happen. There's an error here somewhere.
I'm like trying to see if the multiplication did it.
It's probably not multiplication. I think it's all good.
What happens in
Wait, is it mod 25 though?
No, 26.
Or is it mod
Wait, what about
27
zero?
maybe?
Like,
What?
is 0?
Oh.
I don't know, mod.
I'm using 1 through 26 as the representatives for
Okay.
C26. So rather than using 0 as the representative, I'm using 26. It doesn't matter.
But does that mean that you have to?
Let me make
It's like
this.
the coolest application ever is now ruined.
The application is fine. It's some silly numerical error I'm making here on the fly. Let's look at this. I actually have an example here. So Here's a particular, I took a message, I coded it, I just multiplied by the matrix like I was trying to show you. Oh, I guess I can just leave the negatives. Duh. Oh yeah. Okay, sorry. Anyway, and then I multiply by, oh, that's right, because I'm sorry, number theory is corrupting my mind at the moment on this issue. So there's my string of coded messages, right? And then to uncode them, I just multiply by the inverse. And so when I do that, out pops this 19, 19, 0, 3, 1, which then back to the alphabet code is translated to classes canceled. So this was originally a college algebra example. So if you know your audience, you have to give them what they want.
It's part of these thing with other fixes.
Nevertheless, that's another thing you can do. You can take an invertible matrix, take a message, scramble it, and then the inverse matrix, use unscramble it. It's kind of a nice idea. Another important role that matrices play is they allow you to construct basically what are complex numbers. So if you look at the matrix A minus B, BA, and if you look at the matrix X minus Y, YX, multiply these, they multiply the components, the X and the A and the Y and B, they multiply together just in the same way complex numbers multiply. Right? Like if you take A plus IB times X plus IY, you get AX minus BY, and plus I times AY plus BX, right? In the same way, the real part of the thing that corresponds to the real part of the complex number, right, that translates into AX minus BY, just like this and that goes to AX minus BY. In the same way, the B and the Y go to AY plus BX. In the same way here, the B goes to AY plus BX. So you can use 2x2 matrices to encode the algebraic structure of the complex numbers. This is one way you can construct complex numbers. In fact, this is a way you can construct all kinds of other number systems. That doesn't really come up in your coursework that much, but it's true. Now, finally, getting back to what you were asking me about, Landon. The best answer I have to you is where do matrices come up in calculus 3? It really has to do with what's called the Jacobian matrix. So if you have a function from Rn to Rm, you can approximate the change in this function, all right, basically, by this piece here, this so-called Fauché derivative of the function at a point. And this is a linear transformation, and therefore it has a matrix representative. All right? Now, let me put that away. I want to show you a specific example in the 2 minutes that remain. So, just to give you a very, very short crash course in what's the Jacobian matrix, it's really simple, actually, if you've had Calc 3. If you haven't had Calc 3, don't worry about it. I'm not going to test you on partial differentiation. I haven't taught. But here's an example. Phi of, say, z comma theta equal to, I don't know, z cosine theta, z sine theta, z. All right, so phi in this case is a function from R2 to R3. It is not a linear function, right? It's got cosine and sine in it, okay? There's your clue. But you can calculate what's called the Jacobian matrix of P, or as I like to call it, P prime. And what it is, it's simply the matrix partial phi, partial z, partial phi, partial theta. So how do you take the partial derivative of phi with respect to z?
Hold theta constant.
Yeah, hold theta constant. So remember, this is just my silly notation for column vector, right? So you guys tell me, what's partial phi, partial z? Very easy, it's just cosine theta, sine theta, 0. And the second column?
Wouldn't it still be z or something?
Oh, 1, sorry. Yeah, thank you. and then minus z sine theta, z cosine theta. Now it's 0, right? Because partial z, partial theta is 0. Z and theta are independent. And so, in short, now we can talk. Now you guys know about linear independence, right? So linear independence. You talk about linear independence in the Jacobian matrix. It tells you a lot. So like, okay, this is a function from R2 to R3. You can ask like, what does the image of the function look like in R3, right? Is it like a line? Is it like a plane? You know, what's it like? Yeah.
Is the standard matrix of that 1, 1, 1, negative 1, 1, 0?
Standard matrix of what?
That Jacobian matrix.
The Jacobian matrix is the matrix. I mean, it's what you. I don't compute. I mean, if you evaluated a particular point, for example, I mean, technically speaking, I should say at the point z comma theta. Okay. So here's an example. If I look at the point 0 comma theta, what do I get? Cosine of 0. Oh, excuse me. I get cosine theta, sine theta, 1. How about the second column? 0, 0, 0. Yeah. How many linearly independent vectors in the Jacobian matrix at that point where z equal to 0? Just 1. How about anywhere else? Anywhere else? Anywhere where z is not 0, you've got 2 linearly independent vectors. So for z not equal to 0, you can count 2, not minus, 2 linearly independent vectors in the Jacobian. Why is this? I mean, what is this? What is this Jacobian? What is linear independence of Jacobian telling you? What is this example? Let me tell you what it is. What I've done is I've just shown you the parameterization of a cone. This is x is equal to z cosine theta, y is equal to z sine theta, and z is z. So you can easily check x squared plus y squared is what? Is what?
Z squared.
Z squared, right? And I don't know if you know this or not, but that's a double cone, or sometimes just we call it a cone. It looks like, right? This point right here is z equals to 0. So this combination of calculus and linear algebra has shown you, if you study a little bit more, that this cone is a two-dimensional thing locally at every point except for the singular point, where the number of linearly independent vectors in the Jacobian matrix drops to 1. That's all I'm going to say about that here. If you want me to talk about this in considerably more depth, come take advanced calculus with me. We beat this stuff to death. In there. Oh, that's all I have for today. Although I do have you, I have a couple things, homework, and your students. Now, part of the reason I was late was I printed this out. Go tell the math department I printed out a 10-page quiz for you.
I'm sorry.
Is that camera off yet?
Good.